Over the decades, establishing an efficient strategy for landing on the red planet has always required solutions far beyond the conventional. The soft surface, despite being a destination long coveted by travel agencies, spatial, pose unprecedented technical difficulties. Techniques such as the use of large airbags or complex controlled descent mechanisms by cables have already been used in Shadows and rovers. However, these methods, although ingenious, are still far from the ideal point for transporting human beings. Given this scenario, NASA has been developing a new Mars landing system, which is based on the analysis of data from SpaceX. But it gives it very different principles than those initially expected. Surprisingly, this innovative approach may have no direct connection to the Starship itself, while offering essential elements to determine what the Starship will need to face when you finally reach the soft ground. Before understanding the method most recently proposed by NASA, it is useful to highlight the natural obstacles that make the descent to Mars so complex. The main distinction regarding operations on Earth or the Moon is in the atmosphere of the fourth planet in the solar system. This picture created a unique situation. In a courtyard, the air is too thin for the anaerobic space to use strategies based on atmospheric resistance. Like ordinary parachutes, effective aerodynamic braking. On the other hand, it is still dense enough to interfere with descent maneuvers. The air density on Mars is less than 1% of Earth's, resulting in very high terminal velocities, reaching close to an impressive 1,000 kilometers per hour. Approximately 4 times larger than those found on Earth. This reality already challenges NASA, ESA, and Russia, who had difficulty in adequately reducing the speed of spacecraft, and suffered several sound losses throughout the attempts. The soft atmosphere, moreover, creates a problem known as supersonic transition. The technical retroprop that consists of activating motors facing in the opposite direction to the movement to reduce speed during descent is effective on the Moon, where there is no significant atmosphere. However, NASA originally thought that this feature would only work well in the subsonic range. That is, below the speed of sound. On Mars, when the spacecraft begins to interact with the atmosphere, it still travels at supersonic speed. Sonar thrusters of these conditions could be, according to initial concerns, generate instability, formation of shock waves and turbulence capable of damaging the vehicle. The biggest fear was that engine plumes would create areas of high pressure, excessive heating and loss of control, making the retroprop ineffective for posing large ships, heavy and with high strategic value, such as those that will carry human beings. For a long time, this combination of rare atmospheres has, and the need for disaster relief in speeds above sound, left the impression that placing large payloads, structures, and human crew on Mars would be practically unfeasible with the available techniques. However, recent innovations in propulsion, especially those developed by SpaceX, began to challenge these assumptions. Elon Musk's company's experiments have challenged the conventional wisdom, opening space for new approaches and raising hope that technical barriers can be overcome. A turning point in this discussion occurred when Rodman A., NASA Jet Propulsion Laboratory engineer, presented surprising results obtained thanks to the cooperation between the agency and SpaceX. Between 2014 and 2017, SpaceX's Falcon 9 rocket flights have served as valuable testbeds. Equipped with special instruments, these vehicles collected detailed data during maneuvers to enter the Earth's atmosphere. These tests are not intended for use on Mars, but the information obtained about aerodynamic forces with thermal behaviors and dynamic pressures at high speeds were remarkably reminiscent of the conditions expected upon arrival at the red planet. So, without having to send anything specifically to Mars, NASA could study the effects of supersonic straight-line acceleration in a partially analogous environment. The immunological analysis of this data involved complex aerodynamic modeling, reconstruction of flight profiles, and use of thermal images. The results of these studies led to unprecedented conclusions about the dynamics of descent at very high speeds. During the Falcon 9's entry burns, researchers observed shock waves forming around the engine plumes. Unlike the initial growth, instead of destabilizing the vehicle, these waves created a type of aerodynamic shield, reducing turbulence and minimizing heating of the structure. This discovery meant that the use of straight supersonic propulsions could in fact be safer and more controllable than initially imagined. From then on, the path to adapting these techniques to the Martian environment began to become clearer. By understanding how engine plumes interact with the daily flow at extreme speeds, NASA engineers have gained more concrete parameters for designing landing systems suitable for the planet. With the knowledge provided by Falcon 9 data, a concrete possibility opens up to adjust decision strategies, making them more efficient and reliable. However, even with this progress, there are still considerable issues to be resolved before landing a human crew on Martian soil. One of the biggest challenges in the field is piloting and operating a spacecraft of considerable size. How to be chipped by such a tenuous atmosphere? Although it is already enough to complicate the decision, it is not dense enough to allow truly effective aerodynamic braking. Additionally, the aerodynamic control surface, with the fins or stabilizers, the desired effect may not occur at hypersonic speeds in rare and mad air. This raises questions about how to achieve stability and maneuverability during the critical phases of the decision. Another factor that can worsen the situation is the occurrence of frequent dust storms on the planet. These storms not only impair visibility and make orientation difficult, but they can also increase heating and turbulence at atmospheric entry. Sudden changes in wind direction and intensity, known as shear, represent yet another risk of loss of control, especially for a large ship. If the spacecraft manages to overcome these stages and reach the surface, new problems arise. The powerful engines used for landing can kick up rocks, dust, and debris from the ground, damaging essential companions and compromising the reuse of the vehicle for a future return. Therefore, it will be vital to create protection systems against vetoes and develop landing gear capable of handling uneven ground, avoiding structural damage and ensuring a safe and stable landing. In addition to the immediate issues related to landing, there is the challenge of establishing an infrastructure that will facilitate future operations. It is necessary to think about suitable surfaces for landing large vehicles without raising harmful particles. Preparing bases in advance minimizes risk, but there is detailed planning involved. Even though fuel production on Mars, through the use of resources, may be a long-term solution, the logistical and technical complexity. It will be necessary to have well-defined materials, equipment, and processes to store, produce, and supply fuel in a reliable manner. Another limiting aspect is the restricted range of launch opportunities to Mars. Due to the relative orbits of the planets, favorable windows arise approximately every 26 months. This periodicity reduces the margin of error. A failure not only implies immediate losses, but they can also push fixes and improvements 2 years into the future. Therefore, development teams need rigorous planning, robust technology, and a lot of patience, since it is not possible to test ideas in short intervals. Despite these challenges, confidence in the ability to overcome such barriers is based on previous achievements on Mars. Although most of the few successful on the planet involve robots, probes, and rovers, such missions offer valuable lessons. In January 2004, the Pirate Row reached the shore and returned on airbags, landing inside the Gaza crater. A few days later, its GMI Opportunity made a similar landing in another region of the planet. Opportunity has exceeded any expectations of durability, operating for thousands of days and providing information about the geological history of the planet, until they were asked to communicate after a dust storm in 2019. In May 2008, the Phoenix landed on Mars using part of the rare is planned for the Mars Solar Lunar mission, which were previously lost. In August 2012, the Curiosity rover arrived on the planet, using an innovative decision system, which suspended the vehicle by cable before releasing it to the ground. This complex procedure worked perfectly, allowing Curiosity to begin its detailed analysis of the crater. In November 2018, InSight landed to study the interior of Mars, monitoring seismic activity and collecting information about the structure of the planet, until the end of their mission in December 2022. Its goal is to search for signs of microbrain life and examine the ancient habitability of the Martian environment. The coupling of a larger vehicle during landing. The tiny helicopter was later released for test flight. In total, he carried out 72 successful flights, becoming the first aircraft to perform a controlled ratio flight on another planet. The path to landing humans on Mars remains fraught with questions, but the accumulated knowledge and recent innovations. If you analyze remarkable progress, data obtained through the collaboration between NASA and SpaceX, added to the experience gained with robotic missions, offer valuable clues to overcome complex landing obstacles, adjust techniques in comparison to new propulsion system, and prepare for the uncertain conditions of the Martian environment, will be fundamental steps towards a greater objective. Put humans on the surface of another planet, and take a significant step in exploring our solar system. It is clear that a reliable, safe and repeatable method for landing on Mars has been developed. Is an unprecedented challenge. But the space industry has demonstrated on several occasions its ability to break down barriers considered insurmountable. With continuous studies, technological advances, and the desire to learn from each attempt, the expectation is that the knowledge generated by past and present experiences leads to increasingly efficient landing systems. In this way, the dream of taking humans to Mars gradually becomes more tangible. And you, like Elon Musk, think we will land on Mars in the next few years? Or will it still take decades for that to happen? Leave your opinion in the comments. If you like this content, leave your like, subscribe and share. And that's about it for today's episode. Thank you so much for tuning in, and that's all for today's update. If you enjoyed watching and found it useful, please make sure to subscribe to my channel and hit the like button. And if you want to support our channel and if you want to be up to date, you can become an exclusive member, so click on our perks through the link in the description below. Thanks to watching and see you next time.